We're going to talk about factoring polynomials completely today, using some division techniques that we learned yesterday. If the remainder is 0 after you divide two polynomials, in other words, if you divide f of x divided by g of x, and the remainder is 0, we'll call this division the quotient. I'll just use a Q for quotient. So f of x divided by g of x is some quotient that we can either divide using synthetic division or long division, whichever one works. And if the remainder is 0, then g of x is a factor of f of x. And q of x is another factor. In other words, q of x times g of x is equal to f of x. And we'll get right into this with an example. Let's divide 2x cubed minus 9x squared plus 7x plus 6 divided by 2x plus 1. If you were given this third degree polynomial, there's no technique that you know of to factor this at all. So if you're told one of the factors, and if you divide, we're going to have to use long division, and if the result of this long division has a remainder of 0, then you know 2x plus 1 is a factor of this third degree polynomial. So let's go through the long division. 2x plus 1, 2x cubed minus 9x squared plus 7x plus 6. 2x cubed divided by 2x is x squared. Negative 9x squared minus x squared is negative 10x squared. Drop down the 7x. Negative 10x squared divided by 2x is negative 5x. And when you multiply, and subtract, 7x minus negative 5x is 12x, and drop down the 6, and then you have plus 6 at the end, and you will get 12x plus 6, and when you subtract, you'll have a remainder of 0. So 2x plus 1 is one factor of this polynomial, and x squared minus 5x plus 6 is the other. So we'll just say, therefore, 2x plus 1 times x squared minus 5x plus 6 is equal to 2x cubed minus 9x squared plus 7x plus 6. And if you look at this quadratic expression, you know that that's factorable also. And we have a technique to factor the quadratic. So fully factored, this original numerator can be factored into 2x plus 1 times x minus 3 times x minus 2. And that is equal to the original numerator. And now if I wanted to find all the zeros of this numerator, it would be pretty easy without a graphing calculator even. We would find that it would be negative 1/2, 3, and 2. So all zeros of 2x cubed minus 9x squared plus 7x plus 6 are x equals, and I'll just put it in set notation, negative 1/2, positive 3, and positive 2. So we'll get some more practice on this. Let's get a fourth degree polynomial. And here's just a second example. Let's determine whether x minus 3 and x plus 2 are factors of this function, fourth degree, x to the fourth minus x to the third minus 7x squared plus x plus 6. Again, we don't have any techniques in order to factor this fourth degree polynomial. So what we're going to do is we're going to divide this by x minus 3, and luckily we can use synthetic division with each one of these two. It'll just make our job a little bit easier and faster. And so let's find out whether x minus 3 is a factor. So with synthetic division, remember you use the opposite of this number, so you're going to put a 3 on the outside of your L. 1, -1, -7, 1, and 6. We don't need any 0 placeholders. And so when we go through the synthetic division, and here's our remainder of 0. So with the remainder of 0, that means that x minus 3 is a factor of the fourth degree, or in other words, 3 is a 0 of this polynomial. So now what we can do is we can take the result of this, which is x to the third plus 2x squared minus x minus 2. And if x plus 2 is a factor of this fourth degree polynomial, then x plus 2 would also be a factor of the result of this. So let's use synthetic division again on x cubed plus 2x squared minus x minus 2. So all we really have to do is set up another L here. Just makes our job a little bit easier and faster. And we can put a -2 on the outside to see if there's a remainder of 0 here after this division. So let's use synthetic division. We have 1. And here is another remainder of 0. So that means that x plus 2 is also a factor of this original f of x. So the answer is yes, they are factors. And the result of this last division is x squared minus 1. So x squared minus 1 times x plus 2 times x minus 3 is equal to the original function. And then one more level of factoring. We know the difference of two perfect squares, so we can fully factor this fourth degree polynomial into x plus 1 times x minus 1 times x plus 2 times x minus 3. So there are 4 zeros. The zeros are plus and minus 1, -2, and 3. If we wanted to put this into our graphing calculator, it would be a W-shaped graph, and it would go through the x-axis at these 4 zeros. So this is factorable. Using synthetic division, we could find out some of the factors because we had a remainder of 0. So now this leads us to something called the rational zero test. This is really important. This is something very new for you. Rational zero test. Sometimes we're given a higher degree polynomial and we have no idea what the zeros would be if we don't have a graphing calculator to check to see where the x-intercepts are. For example, if we were given this fourth degree polynomial and we weren't told these two factors, we wouldn't really even know where to begin as far as what could be factors or what could be the zeros of this polynomial. So there's something that's going to narrow down our choices called the rational zero test. And what this does, it gives us a list of possible rational zeros. And rational meaning not a radical, not an imaginary zero, just some rational zero. It gives a list of the possible ones. Then we can test each one of them to see if they are actual zeros of the given function. And we can do this using synthetic division to make our job a little bit faster. Like I said, if you use synthetic division, it just makes it a little bit easier. For example, let's say we're given f of x equals x to the fourth minus x cubed minus 5x squared minus x minus 6. We're not told any zeros at all. We're not given the graph. We just have no idea where to start. So we'll list the possible rational zeros. And this is how it goes. The possible rational zeros are all the factors of the constant term, all the factors of a constant term at the end, divided by all the factors of the leading coefficient. That is the rational zero test. That's what you're going to use on any function. So in this particular example, the possible zeros, or rational zeros, are the factors of -6. Well, the factors of -6 are plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. Factors of 6. And you can divide this by the leading coefficient, lucky for us, is 1. So plus and minus 1 is in the denominator. And so now what we do is we go through each one of these possible factors and divide it by, if there were more than one number, we would have to divide each numerator by each denominator. But since we just have plus and minus 1 in the denominator, the possible rational zeros are just these numbers right here. So we can list them. There are 2, 4, 6, 8 possible rational zeros, plus and minus 1, 2, 3, and 6. So there are 8 possible rational zeros in this particular example. And now we're going to see if they really are zeros. So there's a couple different ways to tell whether they are actual zeros. You can either substitute each one of these into the original f of x problem and see if it comes out to be 0, or you can use synthetic division. So either substitute into f of x, and if the result is 0, then of course it's a 0. It is an actual 0. Or, either or, or you can use synthetic division to see if there's a remainder of 0. So I'm going to go through this particular problem, this particular function, f of x, and I'm going to substitute all 8 of these possible rational zeros. I know this gets a little bit tedious, but this just kind of shows or proves the point of what I'm trying to make here. So I'm going to list here at the top the original function that I'm evaluating. X to the 4th minus x cubed minus 5x squared minus x minus 6. I'm going to go through all 8 of these zeros. I'm going to first find f of 1, then I'm going to find f of negative 1, then I'm going to find f of 2, then I'm going to find f of negative 2, f of 3, f of negative 3, f of 6, and f of negative 6. And I just substitute in these values. So we get 1 minus 5 minus 1 minus 6 for f of 1, which is equal to negative 12 if you do the math. So no, this is not one of the zeros of the function. F of negative 1 is pretty much the same thing, except for the odd degrees. We'll turn these minuses into pluses. So this would be 1 plus 1 minus 5 plus 1 minus 6. And if you do that math, you get negative 8. So no, this is not a rational zero. F of 2, substitute 2 in here, and you get 16 minus 8 minus 20 minus 2 minus 6, which is equal to negative 20. So he's not a rational zero. F of negative 2, substituting in, you get 16 plus 8 minus 20 plus 2 minus 6. And when you do that math, you actually do get 0. So yes, negative 2 is a 0 of that function. Now let's try 3. F of 3 is 81 minus 27 minus 45 minus 3 minus 6. Do that math and you get 0. So yes, 3 is a 0 of that function. Substituting in negative 3, 81 plus 27 minus 45 plus 3 minus 6. And you do that math and you get 60. So negative 3 is not a 0. And 6 and negative 6, you get 1296. 6 to the 4th is 1296. 6 to the 3rd is 216. Minus 180, minus 6, minus 6, and that is equal to 888. So no, that's not a 0. And f of negative 6, replace a couple of those minuses with pluses. Plus 216, minus 180, plus 6, minus 6. And you should know that that would even be a bigger number when you're adding a couple of the terms instead of subtracting. So 1332 is that result. So that's not a 0. So what we have is we have a couple of zeros for this original polynomial. And that's one way to figure out if they're actual zeros. And the other way is to use synthetic division. So I just set up a synthetic division. There are 8 of them. So I have 8 synthetic division setups here for this particular function. And I'm going to go through each one of these. And something interesting is going to happen. So that's why I want to show you all 8 of these. So first of all, we're going to see if 1 is a 0. So if we do synthetic division with a 1, we get 1, 1, 0, 0, negative 5, negative 5, negative 6, negative 6, negative 12. Okay, so we have a remainder here after synthetic division of negative 12. It's a little blurry. And what's interesting is this remainder after division is the same thing as what f of 1 turned out to be. Now let's try negative 1 through synthetic division. Using negative 1, we get 1. Oops. So here's our remainder. So of course that's not a 0, but f of negative 1 turned out to be negative 8, and that's what we get as a remainder after synthetic division. Let's try 2. We can do this quickly, hopefully. You're getting fast at synthetic division. So negative 20 is our remainder. So 2 is not a 0. And f of 2 turned out to be negative 20 when we substitute it in. So you can hopefully guess what negative 2 is going to give us, because we know that's a 0 through substitution. And you can stop this at any time, this video, and try these on your own if you want. You don't have to watch me do this. So this has a remainder of 0. With a remainder of 0, this means that this implies that negative 2 is a 0 of the original function. Now we're going to try positive 3, and we already know the answer to this one. This should be a 0 also after synthetic division. So the same thing here, the remainder is 0. So that implies that 3 is a 0. You don't have to do both ways. I'm just showing you that either synthetic division or direct substitution will tell you whether or not these are zeros or not. So if you use negative 3, 6, and negative 6 using synthetic division, I'll just go through this quickly. So if you remember, we had 60 as f of negative 3 using x equals 6. We have a remainder of 888 on this one, and then using negative 6, we're even going to get a bigger remainder. We have a remainder of 1332. So what's interesting is from the original function, f of negative 6 is equal to 1332. F of positive 6 is equal to 888. Whatever the remainder is, that is what the f of x value is. F of negative 3 turned out to be 60. F of 2 turned out to be negative 20. F of negative 1 turned out to be negative 8. And f of 1 is negative 12. And that's how we did the direct substitution in this list. Which brings me to the punchline of the whole day. Well, first of all, let's factor. Let's say f of x is that original one, but if we factor this out, we knew that negative 2 is a 0, so x plus 2 is a factor. Oops, you can't see that. That's the negative 2 is a 0. We found out that 3 was a 0, so x minus 3 is a factor. And then when we did our synthetic division, when we found out that negative 2 is a 0, way back here, this synthetic division gave us a result of x cubed minus 3x squared plus x minus 3. And I'll write this over here so you can read it a little bit better. X cubed minus 3x squared plus x minus 3. And this particular polynomial you can do factor by grouping. So you take out x squared and you're left with x minus 3. Take out a 1 and you're left with x minus 3. And so this factored will be x squared plus 1 times x minus 3. And the original, when we had negative 2 being our 0, we will have x plus 2 as the factor on that. So x plus 2, and we saw that x minus 3 and x squared plus 1 is the other factor of this original polynomial. So the zeros are negative 2, positive 3, shown direct substitution and synthetic division, and then it has two imaginary zeros, plus and minus I. negative 2, 3, plus and minus I, the square root of negative 1. And so the punchline of this is the remainder after division of f of x, like that long fourth degree polynomial, divided by x minus a could be negative 2, positive 3, is f of a. This is something that you should probably take a look at a little bit more, think about a little bit more, but this is a really important aspect of this, the polynomial division. And if you wanted to take a look at this original function, x to the fourth minus x to the third minus 5x squared minus x minus 6. Let's see if I have this in my graphing. Yeah, I have it in my graphing calculator. If you take a look at the graph, you'll see that it goes through the x-axis at negative 2 and positive 3. Those are two of the zeros, and the other two zeros are imaginary. They won't touch the x-axis. And that's it for today.